Okay, today I will show you 4 questions. I'll solve 4 questions for you. I'll start with the first question. At the end of this question, I will stop this section and start. We'll give a break, like 5 or 10 minutes break. Then I'll start the second question, and it will continue like this. At the end of each question, I will give a like 5 or 10 minute short break. So let me start with this one. Let me read the question first. It says a 10 centimeter high bump in a wide rectangular horizontal channel creates a hydraulic jump just upstream with the following flow patterns shown in the figure below. If y3 is 32 centimeter, estimate the velocities and depth at the section 1 and 4. It also says the state any assumption in the solution and indicate the alternate and conjugate depths. Before we start, let me tell you what is alternate and what is conjugate depths. Alternate depths are the depths having the same specific energy. So here in this question, why section 2 and section 4 have the same specific energy. Therefore, y2 and y4 are alternate depths, and conjugate depths are basically the depth of flow before and after the hydraulic jump. Therefore, y1 and y2 are the conjugate depths. If we start solving the question, first of all, we need to assume y3 will be equal to y critical, and therefore this step, this upward step, delta z will be equal to delta z max. Since we assumed y3 is equal to y critical, we can write this equation as y3 is equal to y critical, and as we know, the y critical has this kind of an equation. We can calculate y critical by cube root, inside of a cube root, small q squared divided by 2g. To be able to perform this equation, we need to calculate small q, of course. But don't forget, this is for rectangular channels. What was y3? And it is also equal to y critical due to our assumption. It is 0.32. We know what is g. And here we can calculate q. From this equation, small q comes 0.567 meter cube per second per meter. Since the channel width is constant through this section, all the sections, this small q will stay constant as well. It won't change. Once we calculated this small q, and we know the y critical was 0.32, now we can calculate E3, energy at section 3. Why? Because we, as I said, we assumed y3 is equal to y critical, so energy critical will be equal to energy at section 3. And how do we calculate critical energy? It is 3/2 times y critical. So it will become 3/2 times 0.32, and our energy at section 3 will be equal to 0.48 meters. Once we found this energy at section 3, we can easily calculate the energy at section 4. Why? Because the energy at section 4 is equal to energy at section 3 plus this upward step. So it will be basically 0.48 plus this step. It is 10 centimeters. 10 centimeters is equal to 0.1 meters. Therefore, energy at section 4 will be equal to 0.58 meters. After we find energy at section 4, by using the energy equation for that section, which is y4 plus v squared over tg, v4 squared over tg, of course, we can calculate y4, but we don't know the velocity at that section. Therefore, we will replace velocity with discharge over cross-section area, and we will get this one. And we will need to still replace this discharge with small q times v. because we know what is small q, but and we can use it. When we replace the small q and we put, when we write what is the cross-section area, so basically cross-section area is depth of flow at this section and the channel width, so y4 times b, and the discharge is equal to small q times b. I put them here into equation and we get something like this. This b square and this b square coming from this parentheses will cancel each other. At the end, we are going to left with E4 is equal to Y4 plus small q square divided by 2g Y4 square. We know what is E4. It was 0.58. We don't know Y4. We know what is Q, 0.567. We calculated here. This is 2 times G. So it corresponds 19.62, and we still don't know what is Y4. And from this equation, we are calculating Y4 as 0.211 meters. We said Y2 and Y4 are alternate depths, and the energy at section 2 and section 4 was equal. Therefore, by using this energy, 0.58 meters, we can calculate Y2 as well, same by using the same method that we used in calculation of Y4. So I'm basically writing the same equation. E2 will be equal to Y2 plus small q2 square divided by 2g Y2 square. E2 is equal to Y4, which is 0.58 meters. And we know what is small q. As I said, it won't change through this channel because the channel width is not changing and discharge is constant as well. So we have 0.567 square divided by, this is again 2g times Y2 square. And from here, Y2 is equal to 0.52 meters. Then we also need to calculate flow depth at section 1 as well, because question also asking that. So I'm writing one more time energy equation for section 1, which is y1 plus small q to q square divided by 2g y1 square. I put the known parameters as like small q and this gravitational acceleration. At the end, we get this equation again. We knew energy at section 2 was 0.58, so we know the energy here. We write the energy here, and there's a hydraulic jump. So basically, energy at this section minus the head loss occurring due to this hydraulic jump will be equal to energy at this section 2. So what is the head loss through a hydraulic jump? I wrote the equation here. It's y2 minus y1 cubed divided by 4y1 y2. So here you can see the energy equation between section 1 and 2. So I plug the parameters. So for energy 1, we have y1 plus this term coming from here, minus the head loss. We know y2, it was 0.52. And it will be equal to energy at section 2, which was 0.58. And from this equation, y1 is corresponding 0.18 meters. And as I mentioned earlier, y1 and y2 are conjugate depths. Now we need to calculate the velocities, because question is asking us to calculate velocities. We need to find velocity at point 1 and velocity at section 4. So if we calculate the energy at section 1, and as you know, the energy equation is flow depth plus the v squared over 2g, then directly we can take this, we can calculate this velocity. So let's calculate the energy at section 1, because we calculated y1 and we know small q, so we can find this energy easily. So it will be 0.18 plus 0.567 square divided by 2g times 0.18 square, and it corresponds to 0.686 meters. So this 0.686 meter will be equal to y1 plus v square over 2g. I wrote that here as well. So from here, v1 comes 3.151 meter per second. And to find the v4, I will apply the same method, but the good thing is we already know what was v4 from here, from the previous section. v4 is 0.58 meters, y4 was 0.211 meters plus the v4 squared over, this is 2g, and from here v4 is 2.691 meter per second. This is the first question. Now I'm gonna stop here. After a 10 minutes break, I will solve the second question. See you in 10 minutes. By the way, don't forget you need to come to the second link for the second question.